Unit 6, Physics 2 Foundations here for 2019. Here's your equations. And the first question is all about stars. So we've got red giant and white dwarf. Are you missing words there? And then diagram 2, more massive than our sun. So this needs to be now a super giant and then a neutron star. Could have been a black hole, but the words used up the top, there's no black hole, so the only one was neutron star, which is there. Then underline, and make sure you underline and don't circle. The main sequence star is stable because its gravitational is equal to radiation pressure or gas pressure. It's fusion. For the second one, they generate their energy. And then during the final stages, you've got supernova. And then solar system is the answer to this one there. So fairly simple questions to start the paper off. Then we've got matching the descriptions. Again, I think this is very achievable. Then you've got an equipment list by year. So we've got a ruler, we've got some tongs, some paper. We've got radioactive elements. This measures the radioactivity of radioactive elements. And then we've got a stopwatch. And then it's asking us to come up with some sort of method to collect some data and how it can be analyzed. So the main thing from here that you've got 3 different radioactive sources. So there's one which is only alpha. And remember now, paper blocks alpha. So if you was to stick alpha and then the paper and then this this tube counter, it wouldn't detect any alpha because it's stopped by paper. Now that you know that, you can start thinking about the sort of method that they'd want. There's one then, only beta. Now beta goes through paper. And then the third, it's got alpha and beta. So the way you're going to get marks for this is to use collecting data and then analyzing data as your main titles here. So the first thing, how to collect the data. Well, you're going to measure the background count of the room, and you're going to do that for 2 minutes. You're going to get some sort of number because radioactivity is everywhere. Okay, it'll be a fairly low number. You need to record that number. Then we're going to use the tongs to hold the source close, around about 2 or 3 centimeters, to the tube, and record that for some time. So it's probably the same amount of time. So what you're doing now, you're getting the radioactive source and the measuring device, and then you're going to come up with a figure. Then what you're going to do is then place the piece of paper between the source, and this is like sample 1, and the GM tube for some time, again, maybe 2 minutes, and then you're going to record that. And then you're going to repeat with the other 2 sources of radioactivity. And what this is going to do then, you're able to analyze your results. So you're going to say the alpha source will have a count rate that reduces when the paper is placed between. So if you're recording the alpha without the paper and then with the paper, it's going to drop. The beta won't change at all, so you'll know that that's the beta. And then the alpha and the beta source will be kind of not as high as the beta, but not as low as the alpha. So some of it's going to go through the paper, some of it won't, because alpha doesn't get stopped by paper. A tricky question there, considering that's not on your specified prac sheet. So that's just something you're going to have to maybe think on your feet with. Okay? But the important thing is knowing that alpha is stopped by paper. So I spent a bit of time on that. Then we've come to distance time graph. Oh, sorry, a velocity time graph here. So you've got velocity on the side and then time on the bottom. And then, oh, there we are. I missed a question. No, I haven't missed any questions yet. I've just underlined that because it was relevant. So between which points A to B, B to C, or C to D is the person leaning forward on the Segway. So with this one, kind of relates to the question there because it says you need to lean forward to accelerate it. So it's going to be A to B, between which points A to B. So A to B accelerates. It says there accelerates because he's leaning forward. Okay. And then we're going to get some information from the graph. So I've got 6 here during the first 3 seconds. So acceleration is change over time. The time is 3 seconds because it tells me there. What's the change in velocity? Well, when I look at 3 seconds, it's going to be 6 meters per second. That's why I've done that. It comes out, acceleration is 2, and then the unit is meters per second squared, because acceleration. And then we've got a mass there that we can use. Resultant force equals mass times acceleration. So we've got our acceleration, which is 2, and then we've got our mass, which is 110, and that comes out to be 220 newtons. Nearly there. Okay, so for this one, there's a reaction time. Oh, it's the same question. So it says reaction time of the person riding the Segway is 0.6 seconds. Use a page at which the emergency stops. So we can see that he stops at 9 seconds. Okay, because he's decelerating, so he's trying to stop. But we need to add that reaction time, or take that reaction time off, sorry. So 9 minus 0.6 is going to be 8.4. Because that's the point it would have reacted to it if he's pressing the brake at 9. So his reaction time is 0.6. So 0.6 seconds before the 9, he's going to, that's when he wants to stop. However, he actually stops there because you've got that thinking time before. Actually thinks before he stops. A student states that during the Segway training session, balance forces act on it for 11 seconds. Explain whether you agree or disagree. Well, I don't agree because it's accelerate them for the first 3 seconds. Okay, so it's not 11 seconds there. So it's accelerating for the first 3 seconds. It's constant speed there. Okay, so the forces are balanced from here until there. I'm assuming that's the same sort of shape as the other graph, sorry. So I should have referred to this graph. So the forces are balanced there. It's just the way I've photographed these. And then we've got another graph there. The graph below shows shows 3 possible training sessions carried out. Okay, so we got A by here, we got B, and then C. And then the question is, explain whether you agree with Lucy, because Lucy says that graph C would represent the emergency stop carried out on an icy pavement. So on an icy pavement, it's going to take longer to stop. And yes, so we would agree. On an icy, that looks like kilograms, isn't it? I've got to be careful the way I write by here. On an icy pavement, it is harder to slow down, so the stopping time is longer. So the claim is correct. Question 4 then. So we've got 2.5 meter long track. We've got some results. Identify the control variable on the table. So the thing that we keep the same all the time is going to be the length of the track. So the distance traveled. Use the equation to calculate the mean speed of the toy car on a set height of 10 centimeters. So let's have a look at how long it took at 10 centimeters. 10 centimeters, the mean time was 4, and the distance of the track is, as we know, 2.5. It says there, ba-boom. That's where I got this data from. So distance traveled, 2.5 over the 4. That gives me the answer there. 0.625 meters per second. Describe how the mean time changes as the height increases. So it's decreasing at a decreasing rate. Okay, there's smaller intervals. How do I know that? I can see that it's decreasing, but it's smaller intervals. So the drop from 4 to 3.1 is 0.9, and then the drop from 3.1 to 2.5 is less than that. So that's how it's a decreasing rate. Describe how the mean speed changes as the height increases. Well, it's going to increase. One student says the most repeatable data for the height is 50 centimeters. Explain if this is incorrect. Well, we're looking for the smallest range. If something's repeatable, it means that you get pretty much the same results to the same degree of accuracy. So you want that sort of a small range there. So I've said 10 centimeters has got the smallest range, not 50. Let's have a look. So the range between the result, see they're all pretty similar, 4.0, 4.1, 4.0. So that's a range of 0.1 there, whereas they said 50. Well, look, they're all over the shop. You got 2, you got 1.8, you got 1.9, so that means 1.9. So there's more of a range. Although it's not a massive range, but it's certainly bigger than the 10 centimeter one. Explain why using a timer connected to a light gate is better, because it's going to reduce that human error, and you're going to get more accurate results. So a light gate is like a sensor. So its technology is going to be recording it rather than human. And then we've got a woman jumping from a tall tower and safely lands. I'm glad she safely lands. Let's have a look here. So I've got a weight of 550 newtons. So I'm always looking for things that I can relate to the question. On Earth, the object is 1 kilogram. And it's got a weight of 10 newtons. So that's important because anything now I need, so 1 kilograms, I'm going to need to times by 10 newtons to get that weight. So what we've got is, actually the reverse by here, because calculate the mass of the woman. Well, the weight is 550 newtons, okay, and we know that 10 newtons is 1 kilogram, so we can just divide that 10 into 550 to get 55 kilograms. And we can simply rearrange weight equals mass times gravity. The gravity is 10 newtons, or 10 meters per second squared. So if we know that, then 10 goes into 550 to give us 55 kilograms. She hits the airbag with 5.6 kilojoules of energy. The airbag stops her distance of 2.8. So convert that into joules. So we're going to get a kilojoule. A kilojoule is big into just a normal joule into small. So be smart, mate. Stop being dumb. I'm going from big, which is a kilo. Think of a kilometer is bigger than a meter. So a kilojoule is bigger than a joule. So I'm going from big to small. So I multiply by 1,000 this time. So that multiplied by 1,000 is going to give me that in joules. And then I can use the equation now to stick the work done, which is also measured in joules, over my distance that it gave me there to give me 2,000 newtons. It's suggested that it would be safer if it was filled with water. The distance to stop then is 0.8 instead of 2.8. So reducing the distance is not good, really. So it's not going to be safer because you've got the same kinetic energy, so you've got the same work done, but you've got a smaller distance now. Therefore, with a smaller distance and the same work done, so if this was 10 and this was a smaller distance, you need a bigger force to get the same work. So you can think of this now, if this was originally 10, so 1 times 10 gives me 10, but then as I increase the force, 2 times 5 gives me 10. So as this goes up, this comes down. So if this comes down, this goes up. Therefore, I disagree because a larger force is going to hurt more. It's going to cause more damage. It's not as safe. So here we have some coins, and we're going to model radioactive decay. So it's all about pattern spotting. You can see that it's always starting with 200. So 200 minus 104 is going to give us 96. 200 minus 149 is 51. 200 minus 174, and so on and so on and so on. So there's the pattern to spot there for 1 mark. After 2 throws, the number of coins was 51. How many would you expect? Well, after 2 throws, so one half-life is 100, and then half of 100 is 50. So after 2 throws, you'd expect it to get to 52 half-lives. After how many throws will the number fall to 1/8 of the original number? What I've done there is just a quick, so it starts 1/1 with 0 half-lives. 1 half-life is a half, obviously. 2 half-lives is a quarter, which we just talked about. So then 3 half-lives is an 1/8. Then everything on this side's got to add up to this side. So 14 plus 0 gives me 14. 7 plus minus 1, so 7 minus 1 gives me 6. 2 marks. Nearly there, nearly there. And then we've got this last question then, which was a bit of a stinker. So this is going to be the first question on the higher paper. So the first thing you're going to have to do is to draw the graph in. You get some marks for that, so that's great. And then you're going to have to number spot again. So we've got them all starting with 800s, and then 800 minus 360, and so on and so on. Okay, so very similar pattern to what we saw before. Then we've got a question really asking us what is half-life. It's the time taken for the mass activity to decay by half. And then use the graph to determine the half-life of carbon-14. So when I use the graph now, I can see that it starts at 800 counts. So I'm going to come 400 and then come back. And then it's going to be sort of 6.5 on my graph. What did I put? 6.5, yeah. Now, this question here is not a nice question. Not a lot of people got this right. It was all about ratios. It was about understanding now that you can use this graph to estimate whether this claim is correct. And I talk about this more on the higher paper. So I'm just going to leave this for the higher paper. I can see we're nearly 16 minutes in now. So if you really want to understand this question, which nobody really did, go to the first question of the higher paper for this year, 2019. I hope you've got something out of this, and obviously any questions, come and see me.